Hi, in this video I am going to discuss Edexcel IAL Physics Unit 3 May 2023 paper. See the description of this video. Uh, the link for complete lesson in Unit 3 is given. It's better to see the video, that is a complete lesson in Unit 3, before watching this video, because in that video which is named as complete lesson in Unit 3, I discussed the error calculation, how to find the uncertainty, percentage uncertainty, and also a few practicals, how to rearrange the equation such that you get the equation for linear graph, right? Also, by using the playlist of this channel, you can navigate to any video related to mechanics, mathematics, mechanics M1, mechanics M2 and M3 also, and you can navigate to any video lessons or past papers related to physics, IAL, Unit 1, Unit 2, Unit 3, Unit 4, Unit 5 and Unit 6. So those could be reached by using playlist of this channel. Okay, first question, ruler photograph is given. A student made measurements of the ruler shown. She used a micrometer screw gauge to measure the thickness T at the center of the ruler. So here you can't say repeated measurement, because if they ask student wants to measure the thickness of the ruler, means there you can say the micrometer screw gauge should be used to measure the thickness of the ruler at different points, different orientation. But here its specific region, specific point, at the thickness is measured only at the center, so you can't say about repeated measurements mostly. Anyway, the diagram below shows the reading on the micrometer screw gauge. So a diagram is given like this. So there the readings are shown like 0, then a line, then here, then a line here. So then yeah, so like, so on here you can see the division which is coinciding is 22, is it? So what's the reading they are asking? What's the reading of this thickness? Means, you know what is marked here, the small lines indicates 0.5. So this is 0, 0.5, 1, 1.5 is visible. 1.5 is visible. So the line which coinciding with this horizontal line on the cylinder is 22nd division, and we know the least count of the micrometer screw gauge is 0.01. So the thickness is given by a part. Thickness is given by 1.5 millimeter plus 22 into 0.01 millimeter. So that will be 1.72 millimeter. That's the thickness. Okay, so second part, determine the percentage uncertainty. You know, percentage uncertainty should be given in two significant figures. So that is A part, first part, what I calculated is A part, first part, first question, A part, first part. Second part, percentage uncertainty is given by uncertainty. So micrometer screw gauge least count or resolution is 0.01, half of it, 0.005 millimeter over measurement, that is 1.72 millimeter into 100%. So that will be 0.29 percentage should be given in two significant figures. Okay, so the third part, explain how she should reduce the source of error in this measurement T. So the third part, how to reduce the error. So don't tell about repeat the measurement at different points, because the student wants to measure the thickness only at center. So repeated measurement we can't say. So there is no random error. Random error could be reduced by repeated measurement. So we can't discuss about random error here. This is only about the systematic, possible systematic error. So check for zero error. You have to say check for zero error to remove, check for zero error to remove the systematic error. Okay, so normally if you have zero error, we have to do the error correction, positive zero error correction, negative zero error correction. There are two different types of error corrections. Those are not in your syllabus. So you should say just check for zero error. Third part, check for zero error to remove the systematic error. So systematic error we don't reduce. And the random errors we can reduce by taking repeated measurements. So systematic error means you have to completely remove it. So if the micrometer screw gauge has zero error, you have to do either error correction to remove the zero error, or you have to replace the micrometer screw gauge with the proper one. So here the answer for, I'm not writing it, third part, check for zero error to remove the systematic error. Okay, the part, this diagram is given. The student balanced the ruler on a pivot as shown and recorded the position of the center of gravity of the ruler. So, you know, if you have a ruler, even if it's 10, or just if you have just a ruler, if you balance it where it balances, that will be the center of, where it is balancing, that will be the center of gravity. So they are balancing the ruler on a we call knife edge or fulcrum P. That's a pivot. Where it balances, that's the center of gravity. Normally center of gravity we denote by capital G. So we can say this is the point at which the ruler is balancing. Most probably it will be 50 centimeter mark or slightly less or more. If the ruler is uniform, it will be at 50 centimeter mark, it will balance it. So student is given a 20 gram mass and he wants to find the mass of the ruler. Okay, 20 gram, only just one 20 gram mass is given, and he wants to find the mass of the ruler accurately. We have to describe the procedure. So I'll draw a diagram how to continue the practical. So the student is given just only 20 gram weight slot, nothing else. So he has to use the same ruler to find the mass. I can draw this diagram, saying name it figure 2. So he can hang the given 20 gram mass at a known distance. So when you hang the mass here, that's a diagram, I drew it again. If you hang the mass here, then the ruler will topple, listen, because it can't balance again at its center of mass. If you hang, when you hang the 20 gram mass on the ruler, you can hang it on the left side or right side. If you hang it on the right side, the ruler will topple this way, anti-clockwise direction. If you hang the mass here, 20 gram, it will topple in clockwise direction. So to balance the ruler again, you have to move the knife edge or the fulcrum or the pivot to a new position such that the anti-clockwise moment provided by the weight of the ruler and clockwise moment is provided by the 20 gram mass what we attach. So if the ruler balances again, the clockwise moment becomes equal to anti-clockwise moment, and if we measure, if you know the distances of x2, which is the distance of the 20 gram mass from the new position of the pivot P, and x1 is the distance of the center of gravity of the ruler from the same pivot. If we know x1, x2, we can use the principle of moment, that is mg times x2, x1 is equal to 20 gram, is it, into x2. So here 20 is in grams, so mg means I don't need to write the gravity, so both are in masses, so the g get cancelled, so I can calculate the mass of the ruler by using this. But they ask me to calculate it accurate value, so nothing else, we don't have any other mass, so we have to repeat the same procedure by keeping the 20 gram mass at different x2. So you have to change the position of 20 gram mass, that is you need to change the x2. After you change the position of x2, which is from there the 20 gram is hung, you have to change the position of the fulcrum or the knife edge or the pivot again such that x1 also changes. So you are going to change the x2 every time and you are going to find the relevant x1 such that the ruler balances at different points on the same pivot. Okay, so you are going to change the x2. x2 is going to be the independent variable, x1 is the dependent variable. So if you want, you can plot a graph. One method to find the mass of the ruler, or you can calculate the mass of the ruler from each reading and find the mean value. Either way you can give the final answer. Okay, you can plot a graph, right, for different x2, that's the independent variable, x1 is the dependent variable. You plot a graph of x2 and again I'll show that way you can plot it, or you can calculate the m value. For each value of x2 you are going to get x1 value, calculate the m value, then find the mean value of m. That is one method. If you are plotting a graph, this is the independent variable, x2 is the independent variable, x1 is the dependent variable should be on y-axis. So make the x1 subject, so x1 is going to be 20 over m, we'll mark the mass of the ruler m naught, so EC m naught, g I don't need to put because this is in mass, so this also could be the mass m naught into x2. So plot a graph, this is on y-axis, this is the gradient because both are constants, this is on the x-axis. So when you plot a graph, it will become x1 on y-axis, x2 on x-axis, it will be a straight line through the origin. Find the gradient. Okay, so gradient will be equal to m equal to 20 over m naught. From that find the m naught, that is 20 over m. So you have to describe this in the B part. So that's a 4-mark question. So you have to describe the procedure. So what could be the first point? I already explained the whole procedure and how to get the accurate value for mass of the ruler. Okay, so this first method, without graph, we find different sets of x1, x2 and we calculate each time the mass of the ruler, then find the mean value. The second method, up to here the same, here we are going to tell about graph. So the third point, I'll say this one will come to third point, this will come as a third point. So I'll write the next method, the graphical method. Okay, so this is the second method where we describe by using graphical method. Either way, we can give the answer. Okay, question number 2, I just drew the diagram, it's given there. A student investigated the properties of a solar cell. He illuminated the solar cell using the apparatus shown. So there's a convex lens, there's a solar cell, there's a filament lamp connected to a 12-volt power supply. Explain the purpose of the convex lens, that is a part, first part. What's the purpose of the convex lens? So you can say if the convex lens is not there, the light from the filament lamp will spread out everywhere and the intensity of the light falling on the solar cell will be lower, not enough to produce enough voltage. So what's the purpose of the convex lens means? You can say without convex lens, the light will spread out. The convex lens will converge. Without, you can say the first point, I'm not writing it. Without the lens, the light from the filament lamp will spread out. But when a convex lens is kept, convex lens will converge the light to a point on the solar cell. Why we want to do that? To increase the intensity of the light falling on the solar cell. So again, I'm saying without convex lens, the light from the bulb will spread out everywhere. So the convex lens will converge the light on the solar cell in a smaller region or point. That will increase the intensity of the light. That's the answer for A part, first part, question number 2. A part, second part, the power supply provides a constant 12-volt potential difference. So I'm reading now second part of the question number 2. So the power supply provided a constant 12-volt potential difference across the filament bulb. Describe 2 more ways to keep the light intensity incident on the solar cell constant. So first you can say we should keep now the bulb is giving constant intensity because they are giving constant voltage, right? So the brightness of the bulb remains the same, but we have to keep the light falling on the solar cell at constant intensity. How can we keep it? First, we should say the solar cell should be kept at the same distance from the bulb. So keep the solar cell at the same distance from the bulb. Second point, that's the first point. What could be the second one? They are asking to give two reasons. So second one, we can say control the background light. So that means if you are doing a practical in a just open environment, or there's light coming, the daylight is falling or coming into the room, means the brightness of the daylight could change depending on the cloud, is it? So better do this practical in a dark room to control the background light. So you can say keep the if you do this practical in a dark room, there won't be any other light other than the light from the bulb. So to keep the intensity of the background light constant, do this practical in a dark room. Okay, we can tell these two things. Okay, B part. Okay, I'll raise this. Okay, second thing, the student investigated how the potential difference across the solar cell varied with current through the solar cell. This is the B part. The light intensity inside of the solar cell was kept constant during the investigation. We already described. That is the second part, how to keep the intensity constant. The diagram for the investigation is shown below. So maybe they are trying to analyze. So the intensity of the light falling on the solar cell remained constant, means the EMF, is it EMF produced or generated by the solar panel is remaining constant, but they are going to measure how the potential difference across the solar cell varies with the current flow. So for that they put a variable resistor here and there's a resistor here. They are going to do a practical how varies V, the potential difference across the solar cell when the current flow varies. How can we change the current flow? By changing the resistance of the variable resistor. The total resistance of the circuit could be varied. When the total resistance of the circuit varies, the current flow will vary, and they are going to measure the potential difference across the solar cell. Same thing like what we do the practical measuring the internal resistance of a cell. Same setup we do, is it? The same diagram they have given. So here add to the diagram to show how ammeter and voltmeter should be connected. So ammeter should be connected in series. Draw the ammeter somewhere here, and the voltmeter should be drawn across the solar cell. Right, that part over. That is the answer for B part. First part I drew it. These are the answer for B part, first part. B part, second part, suggest a reason for using a fixed resistor in the circuits. Same question comes with the practical related to unit 2 electricity, how measuring the internal resistance of a cell. Because here we are going to vary the resistance of the variable resistor. By varying it, we are going to change the current flow, but accidentally the RV could become 0. So if the RV becomes 0, the total resistance will become 0 for the circuit, that called short circuit. So if the circuit becomes short circuit, high current will flow and it could damage the solar cell. So to avoid that, there should be a low resistance, something like 20 ohms, something like that we have to attach. So the answer for B part, second part, when RV is varied, there could be short circuit, or the circuit should become short circuit, or to avoid short circuit. When RV is varied to a lower value, to avoid short circuit, there must be a low resistance, because you can say if there is short circuit, current flow, high current will flow and it could damage the solar panel. So you can say the final I am telling. To avoid short circuit, there must be a resistance, low resistance, because if there is short circuit, high current will flow and it could damage the solar cell. That's the answer could be given for. Suggest the reason for fixing a resistor, this one. Okay. Now C part, that is IGCSE type question. Solar cells are used as source of electrical power. Describe two advantages of using solar cells to power a small water pump. So that is means something like a renewable energy. Solar cell is using a renewable energy. So you can say the sunlight is a free energy source. You can say one mark. Then you can say the energy from the sun never produces greenhouse gas. You can say third. You can say sun. The energy from the sun is renewable. Those are the answers we can give for C part. Okay, so almost this diagram is given there. It's actually an electron diffraction tube. It's a good experiment to show that electrons have wave nature. Electron will be emitted from the cathode. This is cathode, this is anode. When the cathode is heated by a heater, this is a heater, due to thermal excitation, we call thermionic effect, electrons will be emitted. Those electrons will be accelerated by the voltage applied across cathode and anode. So high voltage normally we apply between cathode and anode. Anode will be kept positive. So the electrons will accelerate towards the towards anode and pass through the hole, and they'll pass through. This is graphite film, a thin graphite film. So after passing through the graphite, they when they pass through the graphite, interatomic spacing of the graphite, they behave as wave, and due to superposition they form circular ring patterns on the zinc sulfide screen. So they form circular ring patterns, something like this, concentric circular ring pattern, something like this on the screen. Okay, so that will be formed on the screen. It's a curved screen, not a straight screen. It's a curved screen. Okay, so the first part question, A part, the student used vernier calipers to measure the diameters of the rings on the curved screen. A part, first part A part, first part A part, question number 3. A part, first part. Give two reasons why vernier calipers are more appropriate for these measurements than the transparent ruler. Okay, imagine if the screen is flat, we can easily use a meter rule. Only thing, we should ensure the ruler is passing through the center of the circular ring. Say for example, if you want to measure the diameter of the largest ring, so I'll remove all these things. I should keep the ruler something like that. The ruler pass through the center. Eye level, I should judge the center. So I should keep mark two upper points on the opposite ends of the ring if it is on a flat surface, not a curve. This is a curved one. But if it is on a flat scale, I can keep the ruler something like this. And keep the ruler something like this, and I can take a reading between this point and this point. Also, I can change the orientation of the ruler once I can keep the diameter. Only thing, the ruler should pass through the center. Then I can keep the ruler something like this way, is it? And keep the reading here and here, and I can find the average diameter. If it is on a flat surface, we can use the ruler. Only thing, we need to ensure the opposite points, what we consider, should fall through. If I connect the line of the opposite points, that line should pass through the center. So then I can keep the ruler such that the ruler also passing through the center. I can measure the diameter, different orientation to find the average diameter. If it is a flat screen, what I am telling is true, but it is a curved screen. So the circular rings are formed. Say for example, this is a point on the circumference, this is the next point on the circumference. This is curved screen. If you try to keep the ruler here to measure the diameter, ruler will touch only the center of the screen. Like this it will touch. Difficult to get the readings here and here because the ruler will not touch. You can use a set square, but keeping a set square is also difficult there because the edge, the rim of the screen will not allow to keep the set square also. So which instrument is suitable to measure? The vernier caliper, because vernier caliper has two jaws. Yeah, we keep the objects between the wire or whatever, we keep them between the two jaws. So we can keep one tip of the jaw here, something like this. Then the next tip should be kept here. This is the vernier caliper. So I'm not drawing the full diagram, I'm just showing the block diagram of it. Okay, if I keep the two tips of the jaws of the vernier caliper such that those are on opposite ends of a circumference, opposite ends. So the one jaw, if it is kept, so I'll draw it and again that way. This is the one of the rings. So if I keep one tip of the jaw at this point, the next tip should fall on exactly opposite point. That line should pass through the center. Then take the reading of the vernier caliper. We can measure the diameter of the circular ring. But by using ruler we can't, because the ruler will not touch, any point of the ruler will not touch the circumference of the ring. The tips of the jaws of a vernier caliper can touch on the circumference of 2 points of the circumference in opposite points. We can take the reading by using vernier caliper, one reason. The second reason, if you think about uncertainty, vernier caliper, the reading has uncertainty 0.05 because its resolution is 0.1 millimeter, so it will be 0.05. For ruler, the resolution is 1 millimeter, it will be 0.5 larger. So when we are using vernier caliper, the resolution smaller means percentage uncertainty will become smaller, because uncertainty will be half of the resolution, 0.05. So percentage uncertainty also will become smaller. These are the two advantages when we use vernier caliper. Okay, so second part, describe how the student should measure the diameter of a ring as accurately as possible. So I am not writing it. Keep the vernier caliper such that the tips touches the ring at different orientation. Take the diameter at different orientation and find the mean value. So you can say keep the tips of the jaws touches at opposite ends of a ring at different orientations and measure the diameters, plural, and find the mean diameter. That's the answer for A part, second part. Okay, B part, the student used the diameter of the rings to determine the wavelength lambda of the electrons. Wavelength lambda means that's a de Broglie wavelength, lambda equal h over mv, given in the data sheet. He repeated this for two more values of V. V is the voltage. I drew it there. Voltage, which is used to accelerate the electrons from cathode to anode. They gain kinetic energy and the speed increases. So the V is the voltage between, high voltage applied between cathode and anode. The student also determines the value of constant A using the formula. That formula is new. I told that in the lesson called complete lesson unit 3. They can give a new equations, but you will be guided how to approach, how to use these equations. So this is a new equation. They are giving A equal V lambda squared. We don't use this equation in our unit 2 syllabus, but they are giving a new equation, but you can handle it. The results are shown in the table. So they are giving a data collected. Voltage, that is the voltage used to accelerate the electron, 200 kilovolt, 250 kilovolt, 300 kilovolt. So they are lambda, the wavelength of the electron, that is lambda equal h over mv. That is calculated as 2.67, 2.44, 2.14, and the A value is also given 3 different values. So first part, determine the mean value of A. So you know how to find the determine the mean value of A. That is the first part. Mean A is equal to 3 different values. There are no anomaly. All are accepted values. 1.11 plus 1.32 into 10 to the power, I put it as a comment, minus 18 divided by 3. Give the answer the same significant figures or decimal point. We will get 1.22 10 to the power minus 18 meter square volt. Okay, second part. determine the percentage answer. So it's like a values. There are three different. It's a constant. They are saying constant means it should have one value, but three different values are obtained when repeated measurements are taken for V and lambda. So whenever there is repeated measurement, why do we do repeated measurements? To reduce the random error. I mentioned that in my video complete lesson in unit 3. So there are three different values for A. They ask me to find the percentage uncertainty. So we know there's a repeated measurements. We find it by using half, max, minus, minimum. That is the uncertainty. Half, max, minus, min is the uncertainty. Divided by the mean value into 100, that will give the percentage uncertainty. So they ask me to find the percentage uncertainty. So that is equal to half the maximum value of A, that is 1.32. Minimum value is 1.11, 10 to the power minus 18 over the mean value 1.22, 10 to the power minus 18 into 100%. So you will get the percentage uncertainty. We have to give it in three significant figures, 8.6 percentage. 8.6 percentage. Okay, so third part, this answer 8.6 percentage. Different student repeated. So here the student got three different values for A and he found the average value. Different student repeated this investigation using 6 values of V. She plotted a graph of V against 1 over lambda squared and determined the constant A. So instead of finding the mean value of A, repeated data done with different values of A, so different values of V and lambda, you can calculate A, but you can find the average A. But instead of that, that student is plotting a graph of V against 1 over lambda squared. Give two reasons why this is a better method to determine a value for A. Okay, so here also they can ask why the graph of V against 1 over lambda squared is a straight line. They are not asking, but they can ask. The student is plotting a graph of V against 1 over lambda squared. Why is it a straight line? So you know A equal V lambda squared. So that we can rearrange V against 1 over lambda squared. So whatever is said first is on the y-axis. V against 1 over lambda squared. So V is the first they are saying, that is the subject, that should be on the y-axis. V equal A into 1 over lambda squared. A is a constant. So this, if I plot it on y-axis and if I plot this on x-axis, the gradient must be a constant. So you will get a y equal mx format. Gradient gives the A. The question is, why the student is finding A by using a graph? Why can't we find A1, A2, A3 and find the mean value? That is the question. They are not asking this. I just told them. Okay, what's the reason for drawing a graph and finding the gradient? From the gradient we are finding the unknown value. The advantage is, as I said, if you find the values A equal V lambda squared, you can have a set of V values and lambda squared values. Okay, lambda and lambda squared values. You can find the values of A. So there, sometimes the measurement of V or measurement of lambda might have systematic error. The voltage measured, the voltmeter might have a zero error. So if the voltmeter has zero error, all the reading will become larger than the actual value. Say for example, if the voltmeter is reading even when it is not connected in a circuit, the voltmeter is already reading. For example, maybe if we are using analog voltmeter, this is 0, this is 1 volt, this is 2 volt, there is a 0.5 also there. The voltmeter point is at 0.5. So there is a systematic error. So all the readings are going to be increased by this systematic error. Is it? So when you are plotting a graph of V against 1 over lambda squared, right? When you are plotting a graph, sorry, okay. So we'll think about when we are doing calculations. Say for example, so there's a zero error, 0.5 volt. You are getting, for example, the voltage is, for example, 95 volt. You are getting a value of lambda squared and you are calculating the value of A by using this equation. But 95 volt means actually it's 90. I said, okay, zero error is something like, imagine the zero is 5 volt. We'll put it like 5 volt, the zero error. This is 0, this is something like a 10. But the point is somewhere here. We'll make it like a little big value. So we can understand that. So it's at mid of it, is it? So some maybe around 5 volt is the zero error. Even when you are not applying any voltage, the voltmeter is not kept in a circuit, it's reading a value, for example, a 5 volt. That's a zero error, right? So if it is reading 95, actual reading is 90. So the calculated A becomes wrong, not correct, because of this zero error. Same way, later you are calculating 120 volt, lambda squared is measured and you are calculating an A value. 120 volt means actually that is 115 because already it's reading 5 volt, zero error. 5 volt is a zero. Like that, every reading has zero error. So the value calculated by A also going to be zero error. Sorry, also going to have an error due to the zero error when you find the average. But when you are plotting a graph, what will happen? Say for example, you are plotting a graph V on y-axis, 11 over lambda squared on x-axis. Okay, so imagine for a particular lambda squared value. Okay, so for a particular 1 over lambda squared value, the voltage I told earlier, you are getting 95. This is 95. You are marking 95, right? Then 120, something like that. 120, the next reading 120, something like this, 120, right? This is 95. This is 120. Actually, it's 115. So it should go down actually. It should go down actually. So you are plotting a graph something like this. This is the error. Actually, the graph you are plotting. But actual graph should be, how should it be? This should go by 5, is it? 95 should be 90. 120 should be 115. So they all should go down by the same value. Means you will get a graph, actual graph, also straight line parallel to this one. Because all reading will go down by 5 volt. So in this method, when you find the A, that A will have error due to the zero error 5 volt. But here if you find it from the gradient, you won't get that error because actual graph, if I draw, all should go down by 5 volt, that's a zero error. This is the graph you got, the black color graph, both are parallel, both are parallel. So the actual graph and the graph you drew by using, including the zero error, the graph you plotted is black color, both are parallel. So when you are finding the gradient, you will get the same gradient. Even if you find the gradient of this black color line, which includes the systematic error due to the zero error, that gradient and this gradient will be the same, exactly the same, because they are parallel lines. So what's the advantage? Even if there is a systematic error, when you are finding an unknown, you are finding an unknown means that's A, unknown. By using a gradient, the systematic error will not have any impact on that value. You won't get a wrong value. But here, you are going to get a wrong value. We have to put this in sentence. I explained too much, but that means we can simply say a value calculated from a gradient will avoid any systematic error in the final reading or final value. We can tell that. Then what is the advantage of drawing graph? Means any anomaly. So there could be some anomaly, but when you are finding the mean value, it's difficult to find the anomaly. But when you plot a graph, the anomaly could be easily identified. Say you are plotting a graph, you are getting reading something like this. This is the basic line. So this we know anomaly. We don't need to include it. Totally you can ignore. Those are the advantages of plotting a graph and finding an unknown by using the gradient. Okay. Okay, question number 3, part C. The value of A can be calculated using the formula. So they are giving a formula, new formula, A equal h squared over 2EmV. H is the Planck constant, E is the charge of electron, Me is the mass of an electron. So calculate the value of H in joules second when A equal 1.46. So mass of the electron given in the data sheet, now 9.11 10 to the minus 31 kilogram. E, that is charge of electron, also given in the data sheet. So you can get them from the data sheet. So to find the H, you can say H is equal to cross multiplied 2AE MA square root. Okay, substitute the values. 2 A is given 1.46, 10 to the power minus 18. E is 1.6, 10 to the power minus 19 given in the data sheet. Me, mass of electron 9.11, 10 to the power minus 31 kilogram. Find the square root of it, solve it, you will get 6.5. To give it in 3 significant figure, 10 to the power minus 34 joule second. Okay. Second part, the percentage uncertainty in the calculated value is 6%. So when you come to A2 unit 6, you will calculate the percentage uncertainty, because that's different approach we have to do. That's in unit 6. But here they give the percentage uncertainty, which is 6%. Comment on the accuracy of your calculated value of H. So we know the actual value of H is given in the data sheet. The actual value of H is 6.63. Actual value, I write it here, H 6.63 10 to the power minus 34 joule second. So I discussed this type of few questions in the video complete lesson in unit 3. I'll give the link in the description of this video. Okay, this is the actual value, but you are getting this much. What's the accuracy of your answer? Sometimes they ask that way, or sometimes they ask up to what extent your answer is acceptable. Both the approach is the same to answer that. They can ask, here they are asking comment on the accuracy of your value of H. The same thing they could ask up to what extent your answer is acceptable. Okay, for both we can conclude, we have to give the solution, we have to answer it. That could be handled in 2 different ways. Percentage uncertainty is given, that is 6%. So method 1, there are 2 methods we can adapt. Okay, I mentioned those methods in my video also, complete lesson in unit 3. So method 1, we'll find the uncertainty of this value. So percentage uncertainty is given, so uncertainty in H, that is 6.52 into 10 to the power minus 34 into 6 over 100. So that you will get 0.39 plus or minus 0.39 into 10 to the power minus 34 joule second. Then find the range of your calculated value, that's experimental value, range of H. So range of H means 6.5 to 10 to the minus 34 plus or minus 0.3. 6.5 to 10 to the minus 34 plus or minus this value. If you find, you will get the lowest value 6.13 10 to the power minus 34. From that to 6.91 10 to the power minus 34 joule seconds. Here also joule second to joule second. So this is the range of your experimental value. Actual value is 6.60 10 to minus 34. So check whether the actual value is falling within the range. Yes, this is falling within the range of your experimental value. Therefore, range of the experimental value is correct or acceptable. So after that, you should say, since the actual value of H is falling within range of the calculated. They are not using the word experimental value, calculated value. The calculated value is correct. Value is, that's the answer you should give. Okay. This is the first method. Okay, so method 2, what it says, any measurements have uncertainty. So you can calculate the percentage uncertainty. Then there will be percentage difference compared to your value and the actual value. So it says that the percentage difference must be smaller than the percentage uncertainty. That means if the experiment is done correctly without any error flaws, the percentage difference cannot exceed the percentage uncertainty. If the experiment is acceptable, if the experiment is correct, the percentage difference cannot exceed the percentage uncertainty. That means if the percentage difference is smaller than percentage uncertainty, your experimental value is acceptable. So we will check for percentage difference. Is it? So method 2, we will find the percentage difference between your value, that is your value means the calculated value which is given in the exam paper, that value and the actual value. Percentage difference is, we got 6.5 to 10 to the minus 34, so that is 6.63 10 to the power minus 34 minus 6.5 to over 6.63 10 to the power minus 34 into 100%. So that you will get, if you calculate this, you will get the percentage difference will become, that is equal to 1.7 percentage, which is less than 6%, that is the percentage uncertainty. So since percentage difference less than percentage uncertainty, the calculated value of H is correct. That's the conclusion. Method. Either way you can do. Okay, so this diagram is given in the question paper. So these are two retort stands. There are two pulleys and elastic cord. Center is carrying a 1.2 kilogram mass. So they are measuring the angle theta between the two elastic cord by using protractor, and they are measuring the length of this one x by using meter rule. They are telling it in the question. Student investigated the extension of an elastic cord. She hung a 1.2 kilogram mass from the elastic cord as shown. Identify a health and safety issue and how it may be dealt with. Okay. First issue, you can say the elastic cord might snap. That's dangerous. It can hit your eye. So to avoid, for safety reason, wear safety goggles. So first issue, the elastic cord, I'm not writing it, you can write now. The elastic cord might snap. So to protect the eye, wear safety goggle. That is one mark. Second issue, we can say the 1.2 kilogram might fall down. So wear a safety boots, right? That is the second one. Third point, but not necessary, 2 is enough, but third thing, the two retort stands might topple, because when you pull it, they might topple this way and this way. So to avoid toppling, clamp them by using G-clamp with the table, right? Those are the answers for A part, question number 4, right? B part, the student varied the distance between the two stands to vary the angle theta. So you, if you move this stand further apart, the string will become like this and the angle theta will increase. We bring it closer, angle theta will decrease. So the student varied the distance between the two stands to vary the angle theta. She measured theta using protractor. So the theta is measured by using protractor. For each value of theta, she measured the corresponding value of x with a meter rule. Identify two sources of uncertainty with this method. So uncertainty could give mostly a systematic error. Even though they are using the word uncertainty, it's actually a possible difficulty or error. That is the answer you have to tell about it here. So the answer could be when you are using a meter rule or protractor, the first you can say there could be parallax error. because you are going to hold the imagine if you have done some practicals this type only, you will have the actual experience to write this type of question, answer for this type of questions. Imagine you are holding a ruler between 2 points on the string, and if you are taking reading, there's a probability, there's a possibility there could be zero. You have to keep the zero mark of the ruler here. The final reading you have to take it at eye level, so there could be zero error. Sorry, there could be parallax error. Same way when you are measuring the angle also by using a protractor, there could be parallax error. First difficulty. Second one, when you are taking measurements, you might push it. For example, you are keeping a protractor in front of it. Someday you might push it. Extra force you might give it. So that can cause to change in the length x or the angle theta. That is the second possible error. Third possible error, if the rubber cords are thicker, there will be difficulty where to take the reading of angle. Say for example, you are keeping the protractor, this is the protractor, and this is the zero mark. You are going to measure the angle. So imagine you kept the zero mark here along this way, but you are trying to measure this angle. If that rubber cord is thicker, something like thick rubber cord, where to take the reading? Is it? Which point should I take the reading? Could be a problem. Should I take at the mid or bottom or up? So there could be a problem, right? So those are the answers you have to write. So you can write the answers. I'm not writing something like parallax error when using the meter rule, or parallax error when using the protractor. You can get 1 mark. Then you can say the applying additional force to the rubber cord when measuring the angle theta. That also you can say, you might push the rubber cord. Okay, you can write those things. That's the answer for B part, first part. B part, second part, suggest a modification to reduce the effect of one of these sources. So that means I said you might push it. Is it? You might push it means there you can say when you are taking reading, you can say to avoid pushing it, when you are taking reading of angle by using protractor, ensure the protractor is not touching the strings. So keep it very closely, carefully, but not touching it. You can say that. Second thing about when you are telling about, or you can say clamp the protractor on a retort stand and bring it closer such that it's not touching the strings. You can tell that way also. The next thing about parallax error. So to avoid or to reduce the parallax error, you have to read it carefully at eye level. That you can say, take the readings at eye level to avoid the parallax error. Okay, those are the solutions we can say for B part, second part. Okay, so the C part, the student determined the extension delta x of the elastic cord. So that's the reason they are measuring x. So if you know the initial length of the cord, then each time you measure the length and subtract the initial length from x, you will get the extension delta x, is it? So he measured the delta x of the elastic cord for each theta. The relationship between theta and delta x is given by, so the equation is given. That equation we can get it, but I am not going to show that. By using unit 1, we can get that equation. So cos theta by 2 is equal to mg over k delta x. M is the mass hanging, this is the m, and k is the force constant of the elastic cord. Explain why the graph of cos theta by 2 against 1 over delta x can be used to determine a value for g. G is the gravitational acceleration. So we can ask sometime, why is it a straight line graph? That is cos theta by 2 against 1 over delta x. So cos theta by 2 is the first. 1 over delta x they are telling later. So what is mentioned first is the subject. That should be the y-axis. So make the cos theta by 2 subject, already it's cos theta by 2 subject, 1 over delta x, with that if anything getting multiplied with x quantity, that is going to be the independent variable, if anything getting multiplied, they must be constant because the gradient of the straight line must be constant. So cos theta by 2, so we can write cos theta by 2 is equal to mg over k times 1 over delta x. So this is y-axis, this is on the x-axis, this is going to be the gradient. Okay, so I'll put this as capital M because gradient and this going to be confused. Right, so you can say gradient M is equal to mg over k. So g is going to be m times k over capital M. Hence, we can find the g. Okay. Right, next thing is about a graph. Okay, so this is the table given. So the table what they gave has cos theta by 2. There are 5 values, 5 readings. Delta x also they gave 5 readings, but I didn't write everything. I wrote the maximum and the minimum. 1 over delta x we need to calculate, that also must be written with the same significant figure. The data given all are 3 significant, 3 significant. So you also should give the 1 over delta x. Careful, don't forget to put the proper unit per meter, because this is meter means per meter. Give it in 3 significant figures because they all are given in 3 significant figures. So I didn't write the other reading, we don't need. I'm just using the lowest and the highest value. Right. We need to plot a graph of cos theta by 2 against 1 over delta x. I showed it already. It's a straight line. Cos theta by 2 against 1 over delta x will be a straight line. Okay, how to scale the graph? Okay, so there's a different students, they follow different methods. So I normally draw like this, but first you should know it's not necessary to start from 0. We need to start from 0, whether x-axis or y-axis. It's not necessary to start from 0 because in this question we are not going to use any y-intercept point. In case if you want to find some unknown quantity from the y-intercept point, there it's better to start the x-axis from 0, but y-axis you can start from some other value, right? Because you know the standard equation for straight line graphs, y equal mx plus c with the y-intercept point, or y equal mx minus c, or y equal minus mx plus c. Okay, so in all these things, the y-intercept point c means when x equals 0, the y value is the y-intercept point. That's the definition of c. When x becomes 0, the value of y. So if you want to calculate some unknown quantity from the y-intercept point, okay, it's better to start the x-axis from 0. You can start the x-axis from 0, other values you can put with equal intervals. So y value, it's not necessary to start from 0. You can start from any value even when you need to find an unknown value from the y-intercept point. So when x is started from 0, if the graph is cutting somewhere here, this is the actual y-intercept point. You can read it from the graph. But there's a situation. You are getting the first reading, for example, from 100. The second reading is 105. Third reading 110, 115 or 120, 125 and so going on. But there you need to find some unknown from a y-intercept point. The unknown is falling as c when you rearrange the equation. So there, if you start from 0 to 100, you won't have any data because the first reading is 100. Then 100 from 125 or 130, you have the data, the readings are there. So there, if you scale your graph from 0 to 100, there is no reading. Then you are going to complete all these readings in a smaller region. So that means your graph is going to fall on a small strip of the given grid. That is wrong. In that situation also, you don't need to start the graph from 0. You can start the graph from 100. Then you can scale the x-axis such that you are going to use more than 60 or 70% of the grid. Then you plot a graph. So there the graph where it touches the or cuts the y-axis is not the actual gradient because where the x value is 100. So after that, if you want to find unknown value, you can use this method. Take a clear point on the graph, then get the corresponding y value and x value and substitute in your equation and find the c. If you want, you can take another point from the graph and find another value for c, find the mean value of c. You can do that way. Okay. Otherwise, if you know that you don't need to find any unknown quantity from the y-intercept point, easily you don't need to start the graph from origin. X-axis and y-axis could be started from different values. It's acceptable. Okay. Now here how to scale by using this given data. This is we have to plot a graph of cos theta by 2 again 1 over x. This is the lowest value for y-axis. This is the lowest value for x-axis. This is the maximum value for y-axis. This is the maximum value for x-axis. Okay, how can I scale it? See the grid, given grid. There you can see on the x-axis, you see the x-axis, the grid. So if you consider the x-axis, if we take 10 tiny squares as one division, except the first line, this is the grid, this is the grid, y-axis, I can write here. Except the first line, when you consider 10 small or tiny squares as one division, there are 8 divisions you can mark. Count it and see. Except the first line, if you take 10 tiny squares as one division, there you can consider 1, 2, 3, 4, 5, like 8 divisions you can see. So the one division consists of 10 tiny squares. 1, 2, 3, 4, 5, 6, 7, 8 tiny squares are there, right? So 8, 1, 2, 3, 4, 5, 6, 7, 8. Okay. How to scale these values? Little bit of trial and error. When you are doing trial and error, don't mark anything by using pen on the axis. Okay, so x-axis is going to be 1 over delta x. This is my smallest value. This is my largest value. So we will find what could be the division. Each division, how much should I put? Trial and error, we will find it. So that means there are 8 division. Means the range that I am going to use in this x-axis is from 6.06 to 5.46. So the range 6.06 to 5.46. So subtract it. I am going to calculate what could be each division. Each division consists of 10 tiny squares. So 6.06 minus 5.46 divided by 8, you will get almost exactly 0.075. Okay, 0.075. So here I don't need to start the graph from 0. So I can put the initial value 5.40 if I put 5.40 is the initial point if I put. What could be the next value? If I follow exactly this one, it will be 5.475. I can, but the graph is going to be smaller. So I'm going planning, is it possible to get 0.1 as each division? So if I put 0.1, slightly more than this range, if I put it 0.1 as a division, what will be the last division? 8, I told 8 divisions are there. Will I be able to include this value in my last division? I am going to check it. Okay, for that we will see 5.40 I am going to take that as the first value on my x-axis. So will I be able to include this value if I take 0.1, slightly more than this one, is it? So to get that ideas, we will get it 5.40 I am going to put as the first value plus there are 8 divisions, 8 into, I am going to take each division 0.1 means 0.1 if I put it. How much will be the last value? It is going to be 6.20. 6.20 means 6.606 I can include it. So I am going to take each division as 0.1. So 8.40. Then next one is 8.50. sorry, 5.40, yeah, 5.40, 5.50, 5.60, 5.70, 5.80, this is 5.90, 6.6, then 6.1, 6.20, right? I'm able to put all the values. So this is up to the last line or last edge of the x-axis on the given grid. So my initial value 5.46, 5.40, 5.50, 5.46, somewhere here. Yeah, that's good. Somewhere here it's going to be the first reading, x-axis. The last 6.06, so 5.80, 5.90, this is 6.00, 6.06, this is 6.1, so 6.06 somewhere here. See, out of this 8 division, I am using up to this, more than, I think, 80% I am using it. Okay, this is one of the technique to scale the graph. Same way, y-axis, how can I scale it? Cos theta by 2, the smallest value is 0.891, maximum is 0.938. There also we'll take 10 small squares as one division. So except this first line, how many divisions are there? Count it. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12 divisions are there. So each division consists of 10 tiny small squares. So there are 12 divisions. So this is the first division. I am not going to start from 0, not necessary. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. Okay, these are the 12 lines. I didn't put it equal interval, equal space. It's okay. So there also I'm going to do the possible range and calculate the each division, what could be the each division there. So the range is going to be 0.891 to 938. Those are going to be marked on 12 divisions. So what could be the smallest limit? So 0.938 minus 0.891 divided by 12. You will get 0.0039. Okay, but I don't need to use this value. We'll adjust little bit. What could be the closest next value? You know that when we are scaling anything, we scale the intervals. We scale with either the intervals we use as 1, 2, 3, 4, 5, or 0.1, 0.2, 0.3, 0.4, or 0.01, 0.02, 0.0, like that format. One, like a multiple of 10 to the power n multiple of 1s, or 10 to the power multiple of 2s, like 0.2, 0.4, 0.6, 0.8, the intervals, like we can take as intervals as 0.2, or 5, or we can take 0.5, that format. So here 0.039 we don't take each interval, it's a very unusual thing. But I can take this as 0.0. Is it possible to take 0.005? Is it possible to take? We'll try another, because closest calling. Normally we take, I told that the intervals we take either 1, 2, 3. The intervals are 1 or 2, not 3. Like intervals are 1 or 2 or 5 in their order. 1 means it could be 1 or 10 or 100 or 0.1 or 0.01. That order we use as intervals. Or we can take the intervals as 2 or 0.2 or 0.02, or the intervals could be taken as 20 or 200, like that formats. Okay. Same way, like 5.5, 0.05 of the intervals could be 50 or 100, that's format in the order of 5. So 0.005 if I take it, will I be able to include the last data 0.938? If I start the first reading 0.890, if I put it, the divisions I told there are 12, will I be able to include this one in my last reading? If I take the intervals as 0.005, we'll see that is 0.890 plus 0.005 into 12 divisions. So my final reading will become that equal to last reading will become 0.950. So the last reading will become the value 0.950 That is, my maximum value in the data is 0.938. So I can include 0.938 also here. Okay, we'll think if we include the each division 0.005, not 0.0039. We don't use that interval. So 0.890, next one will be 0.895, 0.900, 0.905. This is going to be 0.910, 0.915, 0.920, 0.925, 0.930, 0.935, 0.940, 0.945, 0.950. So I have included all the points. I can show all the points. Say for example, here I showed x-axis I am using between this point and this point, something like more than 70%. Here y-axis, first reading 0.89, 891, so it is 895, 891 will be somewhere here. I am using here, is it? 0.895 is going to be somewhere here. This one, is it? Then 0.938, so this is 95, 940, 935, 940, 938 somewhere here. See, I am using y-axis between this point and this point, so only this much I am missing. So that means I am going to use the graph somewhere from here to here. So around more than 70% of the graph, more than 70% of the grid is used there nicely. Okay, so that's the way you can scale the graph. Okay, anyway, there are some other teachers teach in different way, but this is a better, I feel this is convenient to decide the scale. First calculate the range, but you don't need to use that range. Sometimes you might get very unusual interval. We don't use this. Then try to get the closest interval for that, such that it falls in the order of 1 or 2 or 5. Okay, that's a better one. Then try to calculate, will I be able to include all the values there? Most probably it will fall within the range. Okay. Okay, so you know how to draw the graph. Best fit line, you know. When you are drawing a best fit line, you have to include all the, best fit line means, it's like this. When you draw a line, something like this, some points might fall outside. The points those are not falling on the line should almost equally fall on either side. That is called best fit line. Okay, you have to draw a line there. This is not a best fit line. If you draw a line something like a graph is drawn something like this is not a best fit line, because there are points falling on the graph, but the points those are not on the line are on one side of the graph. It's not a best fit line. So best fit line means there could be few points fall on the line, but the points those are not on the line should almost equally on either side of the graph. When you are finding the gradient, careful, choose two clear points. Those are not your data. Take two clear points. Those 2 points should be reasonably far away. Don't take closer points. Then draw a right angle triangle and extend those lines until they meet the x-axis and y-axis. Then find the gradient. When you find the gradient, you must include the unit of the gradient also, because you know the y-axis unit. So you are finding the gradient. The unit of the gradient will be equal to unit of y-axis over unit of x-axis. That will be the unit of the gradient. When you are drawing a graph, you must name the axis. Normally students may forget to do. Name the axis and its unit. So here x-axis is 1 over delta x, 1 over delta x. Per meter you have to mention. Here cos theta by 2, that does not have any unit. Okay. So finding the gradient, you have to find the, you have to include the unit also. Okay, so in this paper they ask you to find the gradient. So I told how to find it. So I am not doing it. You know how to find the gradient of the graph. You would use the gradient and try to draw it. So determine a value of g. So I already told that when I discussed part C, I showed it as a straight line. So the gradient, I derived it. Gradient m is going to be, I showed is a straight line equation. Mg, I use capital Mg over k. So you are going to find the G. That's the last part of this question. Last part of this. G is equal to M into K over capital M. So here you need to find the gradient. You know how to find the gradient. The last part K is given. M also given. Find the G. Give the G in 3 significant. Better to give the answers in 3 SF. You will be in safer side. Only for percentage difference and percentage uncertainty, you have to give it in 2 significant figures. All others should be given in better 3 significant figures in paper 3, unit 3. Okay. So that's all discussion of this May 2023 paper. I hope it will be useful to you. You can pass your comments. Okay. Bye.